So I'm going to start recording. Whoops. Let me mention something that I skipped over. I probably mentioned it to you, but I didn't actually show you what the equation was. And it's basically that the affine connection, although it looks like a rank 3 tensor, is not a tensor. And the reason it's not a tensor is that under a general coordinate transformation, it transforms as a tensor, but with an extra term, an inhomogeneous term that's not proportional to the original affine connection. And I can maybe say a little bit about this. There are various ways of writing it. So let me just sort of show you how this works. I'll make this bigger so that it's really kind of clear. Oh, and I just realized I forgot to connect the iPad. Hold on. So here I'm connecting the iPad and starting QuickTime. And file, new movie recording, nuts. Every now and then it just doesn't work. So let me quit QuickTime, start over. So let me just make sure everything is, that I really have this thing. Sometimes the connection isn't perfect. And then QuickTime doesn't work. Oh, I have to start notes though. So let me start notes also. God, all right, I think that's the right place to be. And so then QuickTime, file, new movie recording. Let's see if it works this time. Yeah, it worked this time. Apparently it's the connection just has to be really good, otherwise it doesn't work. So how does a remember what is the affine connection in the new coordinates? Well, it would be E prime, the cotangent vector in the new coordinates times the derivative of the tangent vector in the new coordinates, and then with respect to the new coordinates. And on the other hand, the cotangent vector itself is going to transform properly because it is a tensor. So we have EK prime is equal to this, but now we're taking this derivative of a tangent vector, and so that and so the ith the derivative with respect to I prime is, of course, the derivative with respect to the well, let me see here. It's the L prime derivative, and so we have the chain rule here to get dx prime, and then E prime I is the derivative of En with respect to x prime n. And so we have this complicated expression here. Wow, there's a typo here. Big, big typo. I should have noticed that before I decided to show you this solution. Anyway, the first term well, you know what? I think I'm going to skip this because I thought it was just fine. And now I'm seeing that there's well, all right, let me just say that working, if there hadn't been a typo here, one would have gotten an expression like this. And there are other expressions for how the affine connection varies, but it always has an inhomogeneous term, so it's never a tensor. And I think I'll just leave it at that rather than try to fix this. What I think I might do next is just go back to what we were talking about last time, which was, here, let me move this out of the way. It was, we were talking about parallel transport, and I think we went through this enough so as not to do it again. The curvature then, we went through this yesterday. You compute the change in a vector that's parallel transported around a square. And what we found was that it involved something that was explicitly antisymmetric because this integral is antisymmetric in N and L. And this quantity here then is called Riemanns curvature tensor. You might say, well, what is this sign plus or minus? Well, it turns out that both Riemann and Gauss developed formulas for curvature. And if I'm not mistaken, they chose opposite signs. You know, if you have something that's a curved surface, it looks one way from one side. You look at the other side, it looks exactly opposite. In other words, it looks this way. If you come down looking at it this way, it looks as though it might have one sign, but on the other hand, if you look at it from this point of view, you would get a different sign. And so there's a definite sign in general relativity, and that's the one we'll use. But the plus or minus sign comes in. This plus or minus sign is basically arbitrary. And so but the key thing is that the change in a vector, that a covariant vector that is parallel transported around a square is then, it suffers a change that's proportional to the covariant vector, and the factor of proportionality, well, is actually a tensor of rank 4, and it's called Riemann's curvature tensor. It has various symmetries, though, so there are only 20 components rather than 256. I also mentioned why it is that in general relativity, one always sees an expression of this form, d4th x square root of the absolute value of the determinant. That's because this is an invariant, this is a scalar under general coordinate transformations. And we also reviewed briefly this covariant divergence of a tensor. And when you apply it to electrodynamics, what you get is Maxwell's inhomogeneous equations in generally covariant form. And you see, if you notice, this is an ordinary derivative here because because this is anti-symmetric. And notice that if the gravitational field is weak, then the G is equal to 1, essentially, and the G's cancel, and so you get what Maxwell, Faraday, and Heaviside wrote down. This is the divergence, the covariant divergence of the energy momentum tensor. Okay, and you can make a Laplacian in if you take a scalar field F and you take its covariant divergence, the covariant divergence of its gradient, you get an expression that looks like this, or you get this expression. I rewrote the geodesic section to what I did was I basically dropped the hard way to do it and instead did it the easy way. And obviously, if you can do something more simply, that's a better way to do it. The simpler way is to say that we have a scalar here called dτ. This is proper time of a falling body in a gravitational field, and dτ is then this, and now what we've got here then is dτ is this square root, and so this expression here, let me just follow this curve here. This is dτ squared, and that is divided by dτ squared, so you actually just have dτ. But now in this expression, one can set the variation of this equal to 0, and it's a simpler way of going about it, using primes to denote differentiation with respect to τ. And so then we have the change in the metric, the derivative of the metrics times the change in the position, and xi prime is just dxi dτ, xl prime is dxl dτ. But then we have the variation of these two, and so you have the variation of x, ddτ of the variation of x, and ddτ of the variation of L. But I could have put a 2 here and dropped one of these because GIL is obviously symmetric. Anyhow, going through this, one pulls out the variation of xk and from these, and eventually one gets then the this is called the geodesic equation, which describes how a body falls in a gravitational field, there's this whole right-hand side here is a contravariant vector. The dτ is a scalar, and this is there are inhomogeneous terms that arise from this, and they cancel, and that's why this thing is a contravariant vector. If you consider the particle falling in an electromagnetic as well as a gravitational field, then one has to add into the action Q over C AI dxi. Notice that this is a very simple expression, and it's generally covariant. And when we ask, how is this SA is this part of the action, how does that change? Well, it's the derivative of AI with respect to xk times the change in xk, and then we also have, and what is dxi? Well, we can write dxi as ui dτ. So that's what I've done there. And so we get this expression here. And then what one sees is that the equation of motion for a body falling in a gravitational field, but having charge q, mass m, subject to an electromagnetic field, you get this extra term that comes from here, where F, of course, is the Faraday tensor. The action of electromagnetic field interacting with an electric current is similar to this. It's Q dxi is basically the current, so it's AK JK, and one then derives from that the inhomogeneous Maxwell equations. And I don't know if we have to go through this in detail, but I'll just mention, which we'll get to in a moment, is the action for a gravitational field, just the gravitational field, is the scalar volume element times the Riemann curvature scalar, which is a doubly contracted trace of the curvature tensor. And then if you have weak gravitational fields, you take the earlier equation, which was the geodesic equation, and you drop out the dxi detour, which is the ui terms. You drop them because we're saying the motion is very slow. And then also you write the affine formula for the affine connection, but you also drop the time derivatives of the metric in the formula for the Christoffel symbol. By the way, Christoffel symbol, affine connection, and so forth, they all mean the same thing. And sometimes I call it the Levi-Civita connection, which is another name for it. So in standard relativity, they're all the same. So what we have here then is this expression, and G000 is 0 because we're again saying we have a static gravitational field. And we now imagine then that the metric is the metric of flat space-time apart from a tiny effect due to gravity. And so then we see that the geodesic equation is then this, or equivalently, it's, of course, U0 is dx0 detour. I don't know why I had the U0 in there in the first place. Anyway, so for slow motion in a weak gravitational field, what you've got is this, when that's just Newton's law. And we see that if we re-express G00 in this way. And so one identifies the H00 as Newton's potential apart from a factor of c² and -2. And then you get Newton's equation for a particle in a gravitational field, in the sense that the particle's a distance r from a mass m. And you then have this expression here. And the dimensionless gravitational field is phi over c². And as I said last time, it's very small on the surface of the Earth. It's only 1,000 times greater on the surface of the sun. That's partly because the sun is so big. And on the other hand, on a white dwarf, which is smaller, it's 100 times bigger than on the surface of the sun. Let me now go to this gravitational time dilation, which I misinterpreted last time. the equations that we were looking at were perfectly correct. I was just interpreting them incorrectly. Here, the time interval dt is the time between ticks on a clock in a gravitational field described by the metric GIK. Dtor is the time between ticks measured by a clock far away in the absence of gravity. And so what's invariant is the description in terms of ds squared. And so for the clock at rest in empty space, it's just minus c squared dtor squared. That's dtor is the time between ticks. And for the one in the gravitational field at rest, it's g00 c squared dt squared. And so then what we get is dt is dtor over, remembering that g00 is -1 minus 2 phi over c squared. What you get is this expression here, and phi is negative, okay? In particular, phi for, if you're a distance r from a mass m, I should have used a capital M there, I think, then the interval between ticks looks like this. Well, now, what does this mean? This means that if you're a clock in the gravitational, if you have a clock in a gravitational field at rest, in a strong gravitational field, the time between ticks is huge compared to the time between ticks in a remote clock, and both clocks at rest, of course. And so what's happening is the clock at infinity is ticking, tick, 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 and the clock in the strong gravitational field is going tick, tock, tick, tock. And in fact, if the field is really strong, it can be an enormous difference. And so the time between ticks is how quickly time is passing. And so if the time between ticks is long, that means the time is passing very slowly. And so that's what is going on here. An example is given by the Earth. If you're a height h above the surface of the Earth, the change in the time is given by this expression here, which isn't very much of a change. On the other hand, an hour of proper time would take 7 years to pass on Miller's planet, which orbits the black hole Gargantua in the movie Interstellar. Interstellar is a movie I recommend to everybody. It has a dopey beginning, but after the first 10 minutes or 15 minutes, it becomes really very good. And the reason it's so good is that I think it was Kip Thorne, the Nobel laureate Kip Thorne, who advised the director. And fortunately, the director took Kip Thorne's advice for everything except travel through the wormhole. The director thought that it had to be noisy, like in a New York subway train, and instead, whereas Kip Thorne said it should be totally silent, but the director overruled him, and so you've got all sorts of shaking and clanging going through the wormhole. In any event, the point is that when these astronauts spend an hour or two on, or maybe 4 or 5 hours on Miller's planet in a very strong gravitational field because it's close to a black hole, a huge black hole, for each hour they're in that gravitational field, clocks far away outside the gravitational field tick away like crazy, and effectively 7 years of ticks pass for each year on the planet, on Miller's planet. Anyway, I think I went through that a little too long. Pound and Rebka in 1960 demonstrated this. They used a tower in the Harvard physics department, actually, and they used the Mossbauer effect, which was new at the time, and were able to measure the shift in light falling only 22.6 meters down a shaft. It was basically a staircase, and they found a fractional shift of basically 2.5 times 10 to the minus 15. So that was the first demonstration of the gravitational time dilation, and you also see it. You can see it 1 part in a million or 2 parts in a million. Sunlight from the surface of the sun is shifted to the red by 2 parts per million. Okay, what about Einstein's equation? So now we're getting to the essence of, well, not the essence, but an important application of general relativity. And the basic idea here is that you want a scalar, and so the scalar volume element is square root of the absolute value of the determinant of the metric that's covariant, 2 lower indices, rank 2. d4 x, and then times the Riemann scalar, which is the doubly contracted curvature tensor. And then it has a constant out in front. The constant turns out to be c cubed over 16 pi times Newton's constant. Now, Newton's constant is 1 over the square of the Planck mass. So this, or equivalently, Newton's constant is small, so this, and c is pretty fast. So this constant here is a big number. So the action due to gravity is huge for small gravitational effects, or equivalently, given an action, the gravitational what do I want to say? The action due to a small gravitational effect is huge. So gravitational effects are small, and in fact, that's what we know, namely the gravitational field is quite weak. Here, G is 10 to the minus 39, written in terms of GeV and H bar and C, or equivalently, it's 6.67 and so forth, 10 to the minus 11. Anyway, I don't know how much of this to go through in real detail. Let me go through it quickly and then come back. So basically, what we're going to do is we're going to say that this, of course, is the action in empty space where there's nothing but gravity, and so in other words, nothing but the gravitational field. And so we want to say, well, we want to set the variation of this action equal to 0. And so we look at the variation of the square root of G, and then we look at the other term. The first thing, though, was that I rewrote this a little bit. The Riemann scalar is the Ricci tensor, RIK, contracted with the inverse of the metric tensor. And so the variation of this turns out to be, well, actually, maybe I will go through this in more detail, because the essential element is right here. So the basic thing is that the variation of the inverse of the metric is what we want to look at here. And remember, back when we talked about determinants, we learned that the variation in the determinant of a matrix is the term to the matrix times the trace of the inverse of the metric times the variation, the inverse of the matrix times the variation of the matrix. So the variation of the determinant of a matrix is the determinant of the matrix times the trace of the inverse of the matrix times the variation or the change in the matrix. Okay, so if you apply that to, also, if you know that GIK, GKL is just the Kronecker delta, delta IK, so that's either 1 or 0, and its variation has to be 0. And so that means that the variation of the inverse metric times the contracted with the metric plus the inverse metric times the variation of the metric, those add up to 0. And if you use G lower for this, considered as a matrix, then the variation of the square root of the absolute value of the determinant, well, first of all, it's just working out the square root term. What you get is the determinant divided by 2g, square root of g, variation of the variation of the determinant, and then the variation of the determinant, we use this formula up here, and we get the trace of A inverse, well, that's just G upper times the variation of the matrix, which is GIK. And so this thing is equal to that, apart from an extra det, and that extra det turns determinant of G to determinant of G squared. And then you can cancel some of these because this is the absolute value of the determinant of G, and so one of these things cancels one of those, and then you have a determinant of G divided square root of determinant of G, so you just get square root of determinant of G. Anyway, you wind up with this. So, so what is the variation? Remember, the thing that we're looking at is this, so we have to take the variation of all of that. Well, the variation of G inverse, the inverse metric, times the Ricci tensor times the square root of the absolute value of the determinant of G is, well, it's the variation of RIK times the rest of this, plus this times the variation of G, and then finally the variation of the Ricci tensor. And so if we leave this here, we see we've got two things that we can combine, namely the RIK times the variation of the inverse tensor, and over here, the inverse tensor, oh, wait a minute. Yeah, the variation of the square root of G here, that's this, gives us a variation of the inverse tensor. And so we use this for that, and we get this. And then we have an extra term here. This extra term turns out to be a surface term. And the details are here. So this we can ignore because it's just something that happens at infinity. And so what's left is this. And what that means then is that the change in the action is for changes that are local as opposed to at infinity. It's just given by this. And now, since this is arbitrary, what we get is Einstein's equations. So this is the derivation then of Einstein's equations for a gravitational field. This quantity here, RIK minus a half GIKR, this is called Einstein's tensor. But I don't know if we have to focus on that. The point is, the main thing is the Ricci tensor minus a half the metric times the curvature scalar equals 0, or equivalently, the Ricci tensor is a half the metric tensor times the Ricci scalar. Now, if you take the trace of Einstein's equations, what you find is that in empty space, R is 0, the curvature is 0, and the Ricci tensor is 0. And so everything is 0 in empty space. So what Einstein's equations in empty space are telling us is that in empty space, everything's 0, which is what we expect. But the rest of this is that the actual action, so maybe I should write this here. Let me just see if I can switch maybe to blue here. And so the actual action is the action due to gravity plus the action due to matter. And the matter action is this thing here. It's the integral of the energy momentum tensor times the square root of g d4 x, basically. And so the variation of the matter action due to a variation in the gravitational field turns out to be then this, and consequently then what we get is we don't get that the Einstein tensor vanishes, but rather the Einstein tensor is related to the energy momentum tensor by this factor h pi g over c to the fourth. Then you can once again take the trace of both sides, and you get two more expressions. So this gives you the Riemann curvature in terms of the trace of the energy momentum tensor, and it gives you the Ricci tensor in terms of the energy momentum tensor and its trace and the metric. Maybe I should show you some of these. What we do here is we would raise one index here, and so then we would have basically G, say Li R I K. I don't know why I used, well, all right, let's just do it this way to begin with. Minus a half G Li G I K R equals 8 pi G over c to the fourth G Li T I K. And so this is then RLK. And now this is going to be minus a half delta LK R equals 8 pi G over c to the fourth. And this thing here is, we can call that TLK. Well, it is TLK. Now, if we set L equal to K and sum, then what we get is R. And then here, what we get is minus 4 over 2 R equals 8 pi G over c to the fourth, the trace there. And so this is R minus 2R, so it's minus R. So R is equal to minus 8 pi G over c to the fourth T. And that's this expression here. And on the other hand, we can then rewrite this as RIK is this, which is that, but then we have this minus a half GIKR, but we've seen that R is minus 8 pi G over C to the fourth T, so you get this second term there. So these are basically the Einstein equations that are used in cosmology. The basic equations, namely this one that says how the gravitational field responds to the energy momentum tensor. And what you see is we have this very small number here, G, which is Newton's constant, which is very small, and then divided by C to the fourth, and of course C is huge. Let me just move this over just a little bit because so this tells us that the change in the gravitational field due to even a quite big change in the quite big energy momentum tensor is very small. And you can read this the opposite way. You can say that if you have a change in the gravitational fields, then the change in the energy momentum tensor is very small because you have to divide by this small number, which, oh, I'm sorry, what I just said was silly. Skip that. So as I said, this is these then are the equations for cosmology, and the way they're often used in practical cosmology is one says, well, this TIK is a perfect fluid, and so it's a pressure term times the metric plus the pressure over c squared plus the mass density times these u's, which are dxi, d tau, so they are velocities of the fluid. So one imagines that matter is a perfect fluid. Perfect fluid is something that has that if you're in its rest frame, it's isotropic, it doesn't conduct heat, and it's not viscous at all. So it's just things moving past each other in the night, which like stars that are far apart from each other. So then the question is, what is the energy momentum tensor, for example, due to a non-zero value of the energy density in the vacuum? Well, in this case, then the pressure is minus c squared rho. This is a special case. And in that case, Tij is P Gij, and it's minus c squared rho Gij. This you might wonder, how is it then that the pressure can be negative? Well, the idea is that if the vacuum has a positive energy density, then if you increase space, you've increased the energy, and therefore it's in other words, you could have used this increase in energy to push the thing out, so to speak. So what you've got, in other words, is a negative pressure. What I should have written down here is that pressure, and I'm just going to write it with a squiggle here. It's the partial of the energy density with respect to volume, essentially, and it's with a minus sign. And so the energy is increasing with volume. I should have said energy, not energy density. So the energy is increasing with the volume, and so the pressure is negative. So this is less than zero for if you say that space has an energy density. And that was a surprising discovery that was made about 20 years ago by a group, one of whose principal leaders was a person who gave us a colloquium 2 or 3 weeks ago. He Zoomed us a colloquium from, I think, Maryland. I am terrible with names, and I've forgotten his name. Sorry about that. Anyway, he's a famous Reese, that's his name, Reese. And another group was at Berkeley. So what they discovered was that this dark energy, which can be thought of as a cosmological constant. So in other words, when I wrote this Einstein action, or the matter action, I just wrote it as this, but you can certainly add to R, you can add just a constant, because a constant is an invariant quantity, it's a scalar, and so that's one way of getting a negative pressure. In fact, Einstein did include that in one of his early papers, because he thought at the time he was doing general relativity, which was before Hubble's discovery, he thought that the universe was static, and so he wanted some negative pressure pulling the stars away from us, because otherwise they'd be sucked in and the universe would collapse. And so we introduced a constant. Now what we see is that he was right with that, and that is what we now call dark energy. But of course, we don't know what dark energy is. We don't know what dark matter is. So we are in the dark, so to speak. All right, let me just focus maybe for a moment here on the Schwarzschild metric, which is something it's a solution of Einstein's equations. Remember, I said you can have Einstein's equations, which are the Einstein tensor equals 0, or equivalently, well, I didn't write it down, but if you imagine you have a point mass, and then you solve Einstein's equations in vacuum outside the point mass, the mass m, then what you get is, or a solution to that is, was invented by Schwarzschild, and in his coordinates, the metric looks like this. And then if you ask, well, what is the proper time of a clock at R in Schwarzschild's coordinates? It's given by this, and it's less than the time measured by a clock far away. And in fact, if you get close enough to the mass m such that this thing gets as big as unity, you get 0 here, and then the clock stops. And so that's the idea of a black hole. And what Hawking, back in 1975, showed us all is that the black holes are not black. In fact, that was the title of a colloquium that he gave. I was actually at the time in Paris when he gave the colloquium, but I only learned about the colloquium the day after he gave it. So all I saw was the notice, and I remember the title, Les trous noirs ne sont pas noirs. Black holes are not black. I don't know if he gave it in French, but that was the French title. And the temperature then it's a remarkable formula. It's C cubed, H bar, Boltzmann's constant, Newton's constant, and then the mass of the black hole. And so you see how much physics is involved here. Quantum mechanics, special relativity, thermodynamics, general relativity, and gravity. And then you get a temperature, which is kinetic theory. All right, well, we're basically out of time. I'll see you tomorrow, I hope, at 5 o'clock. I'll post this on YouTube, and you can look at it there. Also, I've been rewriting the class notes and taking out things that were unnecessarily obscure and adding, well, I don't know if I added very much, but I think I simplified things a little bit. Okay, so I'm going to stop now. Wish you all a good night, and try not to catch COVID.